Welcome to the Walton Pie. Today we're going to be talking about rates of change and how we can use them in different fields of study to help us solve problems. So there's a lot of different instances where we would like to know what the rate a certain variable is changing. For example, cops don't necessarily care where you are, but they care how fast you're going. And velocity, or how fast you're going, is the rate your position is changing. And so that actually ties in really well with physics, and physics has a lot of applications with rates of changes. So if we let r of t be the position function in terms of time t, then velocity is going to just be the first derivative of position. If we then look to see what's the rate of change of velocity, well, that's going to give us acceleration. So acceleration is the derivative of velocity, which means it's the second derivative of position. After acceleration comes jerk. So if you ever want to insult someone without them necessarily knowing, you could call them the third derivative of position, because jerk is the derivative of acceleration, which is the second derivative of velocity, which is the third derivative of position. Now, at this point, we might be thinking, okay, that's about as far as we can go, but it turns out that physicists had a sense of humor and decided to participate in the wonderful world of creating wonderful puns. And so the derivative of jerk is snap. Yes, so after jerk comes snap, which is the fourth derivative of position, but then after snap comes crackle. So crackle is the fifth derivative of position, and then after crackle comes pop, which, as you guessed it, is the sixth derivative of position. So don't ever say that physicists don't have a sense of humor.
Snap, crackle, pop, Rice Krispies.
Now, even if you're not a huge fan of physics, maybe, for example, chemistry is your thing, even in those fields, there are applications of derivatives. So if C represents the concentration of a reactant, then the instantaneous rate of reaction is the derivative of concentration with respect to T. There's also the concept of compressibility of a gas, and this is going to be a scalar multiple of the derivative of volume with respect to pressure. So we can always find the compressibility of a gas by doing -1 divided by the volume times the derivative of volume with respect to pressure. In other fields, such as biology, derivatives will show up. So if P represents the population of a species, then the instantaneous rate of growth of the species is going to be the derivative of the population. We also have economics. If C is the cost to produce some number of items, the marginal cost is the rate that costs will increase as the number of items produced increases. So in economics, we can also approximate this by the cost to produce one more item, because some things it doesn't really make sense to only make part of a thing. So what's the cost to produce half another can of soda? That doesn't really make sense. So for a lot of economics, everything has to be in terms of one unit, and you can approximate that using the derivative of the function. I hope you enjoyed this video and that you were able to understand rates of change a little bit better and see how they might be able to be applied in your particular field. Please like and subscribe if you haven't already, and please check out some of my other videos.
Let's go for Kellogg's Rice Krispies. Snap, it's crackle, what a happy sound. You gotta have a crackle or the sound not bound. You begin snap, hop, and cereal, snap, crackle, makes the world go round.